What if the greatest dangers of space exploration aren't the ones we see in movies or read about in headlines? What if the real threats are hidden, lurking in the shadows of the cosmos, waiting to challenge humanity's boldest endeavors? Space exploration has long been romanticized as the ultimate adventure, a journey to the stars filled with wonder and discovery. But behind the awe-inspiring images of distant galaxies and the triumphs of landing on the moon lies a darker reality, a reality filled with unseen risks that could jeopardize missions, human lives, and even our understanding of the universe itself. Today, we're diving into the 20 hidden dangers of space exploration, uncovering the mysteries and challenges that make venturing beyond Earth far more perilous than it appears. From cosmic radiation to the psychological toll of isolation, these are the threats that could shape the future of space travel and the survival of those who dare to explore. Stay with us as we reveal the secrets of the void, and by the end of this video, you'll see space exploration in a whole new light. Now turning to the first hidden danger of space exploration, we encounter an invisible yet formidable threat: cosmic radiation. Unlike the dangers we can see, cosmic radiation is a silent, pervasive force that poses a significant risk to astronauts venturing beyond Earth's protective atmosphere. This radiation, originating from the Sun and distant stars, carries high-energy particles capable of penetrating spacecraft walls and human tissue. Over time, exposure to these particles can damage DNA, increasing the risk of cancer and other long-term health issues. The challenge lies in shielding astronauts from this relentless bombardment. While Earth's magnetic field and atmosphere naturally protect us, spacecraft lack this defense. Current shielding technologies, such as thick layers of aluminum or specialized materials, can only partially block cosmic radiation. For short missions, like those to the International Space Station, the risk is manageable. But for long-duration missions, such as a journey to Mars or beyond, the cumulative effects of radiation exposure become a serious concern. Astronauts could face not only heightened cancer risks but also potential damage to the central nervous system, leading to cognitive decline or other neurological issues. Scientists are working tirelessly to develop better shielding solutions, from advanced materials to innovative designs that redirect radiation away from the crew. However, the reality remains that cosmic radiation is an unavoidable hazard of space travel. As we set our sights on distant worlds, understanding and mitigating this invisible danger will be crucial to ensuring the safety and success of future missions. The void of space may be vast and awe-inspiring, but it is also filled with unseen threats that remind us just how fragile human life is in the cosmos. Now turning to the second hidden danger of space exploration, we delve into the profound impact of microgravity on the human body. While floating effortlessly in space might seem like a dream, the reality is far more complex and challenging. Microgravity, the near-weightless environment experienced in orbit, wreaks havoc on the human body in ways that are both surprising and concerning. One of the most immediate effects is muscle atrophy. Without the constant resistance of gravity, muscles begin to weaken and shrink as they no longer need to work as hard to support the body. Astronauts can lose up to 20% of their muscle mass in just a matter of weeks, making even simple tasks like walking or lifting objects difficult upon returning to Earth. To combat this, astronauts must engage in rigorous daily exercise routines, using specialized equipment like resistance bands and treadmills designed for space. However, even with these measures, muscle loss remains a significant challenge for long-duration missions. Equally troubling is the loss of bone density. In microgravity, bones no longer bear the weight of the body, leading to a decrease in bone mass at a rate of about 1 to 2% per month. Over time, this can result in osteoporosis-like conditions, increasing the risk of fractures and long-term skeletal issues. Scientists are exploring various countermeasures, from high-intensity resistance training to medications that stimulate bone growth, but the problem persists as a major obstacle for extended space travel. Another lesser-known but equally critical effect is fluid redistribution. In the absence of gravity, bodily fluids shift upward, pooling in the head and chest. This can cause facial swelling, congestion, and even changes in vision, a condition known as spaceflight-associated neuroocular syndrome. Over time, these changes can lead to permanent damage to the eyes and brain, posing a serious risk to astronauts' health. Researchers are studying ways to mitigate these effects, such as using lower body negative pressure devices to simulate gravity and redistribute fluids, but the solutions are still in their early stages. The physical toll of microgravity is not just a short-term inconvenience, it has the potential to complicate long-duration missions, such as those to Mars or beyond. Without effective countermeasures, astronauts could face debilitating health issues that jeopardize their ability to perform critical tasks or even return safely to Earth. As we continue to push the boundaries of human space exploration, understanding and addressing the effects of microgravity will be essential to ensuring the health and success of future missions. The challenges are immense, but so too is the determination to overcome them, as we strive to make the stars a little less distant and a little more within our reach. Now turning to the third hidden danger of space exploration, we shift our focus to the growing problem of space debris orbiting Earth. While the vastness of space might seem empty, the reality is that our planet is surrounded by a cloud of man-made debris, ranging from defunct satellites to discarded rocket stages and even tiny fragments of metal and paint. This debris, traveling at speeds of up to 17,500 miles per hour, poses a significant threat to both manned and unmanned spacecraft. The danger lies in the sheer velocity of these objects. Even a small piece of debris, no larger than a pebble, can cause catastrophic damage upon impact. At such high speeds, collisions can puncture spacecraft hulls, damage critical systems, or even destroy entire satellites. The International Space Station, for example, has had to perform numerous maneuvers to avoid potential collisions with debris, highlighting the constant vigilance required to protect both equipment and human lives. One of the greatest challenges is tracking and avoiding smaller debris fragments. While larger objects can be monitored and their orbits predicted, smaller pieces are much harder to detect. These fragments, often less than 4 inches in size, are nearly invisible to radar systems, making them unpredictable and difficult to avoid. Despite advances in tracking technology, the sheer volume of debris, estimated at over 120 million pieces, makes it nearly impossible to account for every potential threat. The problem is only getting worse. With the increasing number of satellites being launched into orbit, the risk of collisions and the resulting debris is growing exponentially. Each collision creates more fragments, leading to a cascading effect known as the Kessler syndrome, where the density of debris becomes so high that it triggers a chain reaction of collisions, rendering certain orbits unusable. This scenario could severely limit our ability to explore and utilize space, posing a long-term threat to future missions. Efforts are underway to address this issue, from developing technologies to remove debris to designing spacecraft with better shielding. However, the scale of the problem requires international cooperation and innovative solutions. As we continue to push the boundaries of space exploration, the challenge of space debris reminds us that the dangers of the cosmos are not just natural, they are also the result of our own actions. The path to the stars is fraught with obstacles, but with careful planning and collaboration, we can navigate this perilous frontier and ensure a safer journey for those who follow. Now turning to the fourth hidden danger of space exploration, we delve into the psychological stress that astronauts endure during their missions. While the physical challenges of space are often highlighted, the mental toll of isolation, confinement, and the sheer distance from Earth can be equally daunting. Imagine being thousands of miles away from home, confined to a small spacecraft with a handful of crewmates, and cut off from the familiar sights, sounds, and routines of life on Earth. This environment can take a significant toll on even the most resilient individuals. One of the most profound challenges is the sense of isolation. Astronauts are not only physically separated from their loved ones, but also experience a unique form of loneliness that comes from being in the vast emptiness of space. The lack of real-time communication with Earth, especially during missions to distant destinations like Mars, can exacerbate this feeling. For example, during the Mars 520-day simulation, participants reported heightened feelings of loneliness and detachment, even though they were still on Earth. This simulation highlighted the psychological strain that long-duration missions can impose. Confinement is another major factor. Living in a small, enclosed space for months or even years can lead to feelings of claustrophobia and stress. The lack of personal space and the constant presence of crewmates can strain relationships and create tension. Historical missions, such as the Skylab program, have shown that even well-trained astronauts can experience irritability and conflicts when confined in close quarters for extended periods. These challenges underscore the importance of selecting crew members who can work well together and maintain a positive team dynamic. The psychological strain of being far from Earth also manifests in unique ways. Astronauts often describe a phenomenon known as the overview effect, where seeing Earth from space evokes a profound sense of awe and perspective. While this can be inspiring, it can also lead to feelings of insignificance or existential contemplation, which can be mentally taxing. Additionally, the constant awareness of the dangers of space, such as the risk of equipment failure or exposure to radiation, can create a persistent undercurrent of anxiety. To address these challenges, space agencies have developed robust psychological support systems. Pre-mission training includes simulations and team-building exercises to prepare astronauts for the mental demands of space travel. During missions, regular communication with psychologists and support teams on Earth helps astronauts manage stress and maintain their mental well-being. Technologies like virtual reality are also being explored to provide astronauts with immersive experiences that simulate Earth environments, offering a mental escape from the confines of their spacecraft. As we continue to push the boundaries of space exploration, understanding and mitigating the psychological stress faced by astronauts will be crucial. The mental resilience of those who venture into the cosmos is just as important as their physical endurance. By addressing these challenges, we can ensure that the journey to the stars is not only successful but also sustainable for the human spirit. Now turning to the fifth hidden danger of space exploration, we shift our focus to the critical issue of equipment malfunctions. In the unforgiving environment of space, even the smallest technical failure can escalate into a life-threatening situation. Unlike on Earth, where repairs and replacements are often straightforward, the challenges of fixing equipment in space are immense and the stakes are incredibly high. One of the most famous examples of equipment malfunction in space is the Apollo 13 mission. What began as a routine journey to the moon turned into a fight for survival when an oxygen tank exploded, crippling the spacecraft. The astronauts and mission control had to work together to improvise solutions using the limited resources available on board. This incident highlighted not only the ingenuity and resilience of the crew, but also the fragility of the technology we rely on in space. The Apollo 13 mission serves as a stark reminder of how quickly things can go wrong and how critical it is to have contingency plans in place. Repairing equipment in space is no easy task. The lack of gravity, extreme temperatures, and the vacuum of space create a hostile environment for both humans and machines. Astronauts must rely on specialized tools and training to perform repairs, often while wearing bulky spacesuits that limit their dexterity. Even something as simple as tightening a bolt becomes a complex operation when you're floating in zero gravity. Additionally, the time pressure to fix critical systems before resources like oxygen or power run out adds another layer of stress to an already challenging situation. Another challenge is the limited availability of spare parts. Spacecraft are designed to be as lightweight as possible, which means carrying extra components is often not feasible. This makes it essential for astronauts to be resourceful and creative when addressing malfunctions. For example, during the International Space Station's early years, crew members had to use duct tape and other improvised materials to fix leaks and other issues. These experiences have led to improvements in spacecraft design, with a greater emphasis on modular systems that can be easily repaired or replaced. The harsh conditions of space also take a toll on equipment over time. Radiation, micrometeoroid impacts, and thermal cycling can degrade materials and systems, increasing the risk of malfunctions. This is why rigorous testing and redundancy are critical in spacecraft design. Engineers must anticipate potential failures and build in backup systems to ensure the safety of the crew. However, as we venture further into space, the complexity of missions and the distance from Earth will make it even more challenging to address equipment failures in real time. As we continue to explore the cosmos, the lessons learned from past missions will be invaluable in preparing for the unexpected. The ability to adapt, innovate, and overcome technical challenges will be essential for the success of future space exploration. By understanding and addressing the risks of equipment malfunctions, we can ensure that the journey to the stars is not only ambitious but also safe for those who dare to venture into the unknown. Now turning to the sixth hidden danger of space exploration, we delve into the unpredictable and potentially devastating threat of solar flares and coronal mass ejections. These sudden bursts of solar activity can release enormous amounts of radiation, posing a serious risk to both astronauts and spacecraft. Unlike many other dangers in space, solar flares and coronal mass ejections are entirely beyond human control, making them one of the most challenging hazards to prepare for. Solar flares are intense bursts of radiation that originate from the sun's surface. They occur when magnetic energy built up in the sun's atmosphere is suddenly released. While Earth's atmosphere and magnetic field shield us from the worst effects of these events, astronauts in space are far more vulnerable. A single powerful solar flare can expose astronauts to radiation levels equivalent to hundreds of chest X-rays in just a matter of minutes. This not only increases the risk of acute radiation sickness, but also raises the long-term likelihood of developing cancer or other health complications. Coronal mass ejections, or CME, are even more extreme. These events involve the sun ejecting massive clouds of charged particles into space at incredible speeds. When these particles collide with a spacecraft or an astronaut, they can cause significant damage. For example, a CME could fry sensitive electronics on board a spacecraft, leaving astronauts stranded without communication or navigation systems. In the worst-case scenario, a direct hit from a CME could even compromise the structural integrity of a spacecraft, putting the entire mission at risk. One of the biggest challenges with solar flares and CMEs is their unpredictability. While scientists have made significant strides in monitoring solar activity, accurately predicting when and where these events will occur remains difficult. The sun's behavior is influenced by complex magnetic interactions that are not yet fully understood. This means that even with advanced warning systems, astronauts and mission controllers must always be prepared for the possibility of a sudden solar storm. To mitigate these risks, spacecraft are equipped with shielding designed to protect against radiation. However, no shielding is perfect, and the weight limitations of spacecraft mean that there is always a trade-off between protection and practicality. Additionally, astronauts on long-duration missions, such as those to Mars, would be exposed to higher levels of solar radiation simply because they are farther from Earth's protective magnetic field. This makes developing more effective shielding and early warning systems a top priority for future missions. Communication systems are also vulnerable to solar activity. High-energy particles from solar flares and CMEs can interfere with radio signals, disrupting communication between astronauts and mission control. This could be particularly dangerous during critical moments of a mission, such as a landing or docking maneuver. To address this, engineers are working on more robust communication technologies that can withstand the effects of solar radiation. As we continue to push the boundaries of space exploration, understanding and preparing for the dangers of solar flares and coronal mass ejections will be crucial. These events remind us that space is not only vast and mysterious but also inherently hostile. By advancing our knowledge of solar activity and developing better protective measures, we can ensure that astronauts are as safe as possible as they venture into the unknown. The Sun, while essential for life on Earth, remains one of the most formidable challenges we face in our journey to the stars. Now turning to the seventh hidden danger of space exploration, we shift our focus to the critical challenge of managing limited resources. On long-duration missions, astronauts must rely on a finite supply of essentials like food, water, and oxygen, making resource management a matter of survival. Unlike on Earth, where these necessities are abundant, space missions require meticulous planning and innovative solutions to ensure that every drop of water, every breath of air, and every bite of food is used efficiently. One of the most pressing concerns is the availability of water. While water is essential for drinking, it is also used for hygiene, cooling systems, and even producing oxygen through electrolysis. On missions lasting months or years, carrying enough water from Earth is simply not feasible due to weight constraints. To address this, space agencies have developed advanced water recycling systems that can purify and reuse wastewater, including urine. These systems are a lifeline for astronauts, but they are not foolproof. Any malfunction could lead to a dangerous shortage, highlighting the need for reliable and redundant technologies. Oxygen is another resource that cannot be taken for granted in space. Unlike on Earth, where the atmosphere provides an endless supply, spacecraft must generate oxygen artificially. This is typically done through electrolysis, which splits water into hydrogen and oxygen. However, this process requires a steady supply of water, creating a delicate balance between water and oxygen management. If either resource runs low, the consequences could be catastrophic. To mitigate this risk, researchers are exploring alternative methods of oxygen production, such as extracting it from lunar or Martian soil, which could be a game changer for future missions. Food presents its own set of challenges. While astronauts rely on pre-packaged meals, these supplies are limited and can degrade over time. Growing food in space is a promising solution, but it comes with its own hurdles. Microgravity affects plant growth, and the lack of natural sunlight requires artificial lighting systems which consume precious energy. Despite these challenges, experiments aboard the International Space Station have shown that it is possible to grow crops like lettuce and radishes in space. Scaling up these efforts to provide a sustainable food source for long missions remains a key area of research. The risks of resource shortages are not just theoretical. History has shown that even small miscalculations can have serious consequences. For example, during the Apollo 13 mission, a critical oxygen tank failure forced the crew to ration their remaining supplies, turning what was meant to be a lunar landing into a desperate fight for survival. This incident underscores the importance of having backup systems and contingency plans in place. To address these challenges, scientists and engineers are developing cutting-edge technologies to recycle and conserve resources. Closed-loop life support systems, which aim to reuse every possible resource, are at the forefront of this effort. These systems not only reduce the need for resupply missions, but also make long-duration space travel more sustainable. Additionally, advancements in 3D printing could allow astronauts to manufacture spare parts and tools on demand, reducing the need to carry excess supplies. As we look to the future of space exploration, the ability to manage limited resources will be a cornerstone of mission success. Whether it's a journey to Mars or beyond, ensuring that astronauts have access to the essentials they need to survive will require innovation, ingenuity, and careful planning. The challenges are immense, but so too are the opportunities to push the boundaries of what is possible. By mastering the art of resource management, we can take one more step toward making the dream of long-term space exploration a reality. Now turning to the eighth hidden danger of space exploration, we delve into the mysterious and potentially perilous world of alien microorganisms. While the idea of encountering extraterrestrial life is thrilling, it also comes with significant risks. Unknown microorganisms in space could pose a threat to astronauts, compromising their health or even jeopardizing entire missions. Moreover, there's the risk of these organisms contaminating Earth upon the crew's return, potentially introducing unforeseen dangers to our planet's ecosystems. One of the primary concerns is the possibility of harmful pathogens that could infect astronauts. In the confined environment of a spacecraft, even a minor illness could spread rapidly, with limited medical resources available to treat it. Unlike on Earth, where we have a deep understanding of most pathogens, alien microorganisms could behave in unpredictable ways, making them difficult to diagnose and treat. This uncertainty underscores the need for rigorous quarantine protocols and advanced medical research to prepare for such scenarios. To mitigate these risks, space agencies have implemented strict planetary protection measures. These protocols are designed to prevent both forward contamination, where Earth-based organisms could contaminate other celestial bodies, and backward contamination, where extraterrestrial organisms could be brought back to Earth. For example, spacecraft and equipment destined for other planets undergo thorough sterilization processes to eliminate any Earth-based microbes. Similarly, astronauts returning from space missions are quarantined, and their samples are carefully analyzed to ensure no alien organisms are introduced to Earth. Despite the risks, the scientific interest in extraterrestrial microorganisms is immense. Discovering life beyond Earth would be one of the most groundbreaking achievements in human history, offering insights into the origins of life and the potential for life elsewhere in the universe. Missions to Mars, Europa, and Enceladus are specifically designed to search for signs of microbial life, with instruments capable of detecting even the faintest traces of biological activity. These missions are conducted with extreme caution, balancing the pursuit of knowledge with the need to protect both astronauts and Earth. The search for extraterrestrial life also raises ethical questions. If we do find microorganisms on another planet, how should we interact with them? Should we attempt to study them in their natural environment, or could we risk altering their ecosystem by introducing Earth-based contaminants? These questions highlight the delicate balance between exploration and preservation, a challenge that will only grow as we venture further into the cosmos. As we continue to explore the mysteries of space, the potential threat of alien microorganisms reminds us of the need for caution and preparedness. While the discovery of extraterrestrial life would be a monumental achievement, it also comes with responsibilities. By developing robust protocols and advancing our understanding of microbial life, we can ensure that our quest for knowledge does not come at the cost of safety. The unknown may be daunting, but it is also what drives us to explore, discover, and push the boundaries of what is possible. Now turning to the ninth hidden danger of space exploration, we encounter the relentless challenge of extreme temperatures. In the vacuum of space, there is no atmosphere to regulate heat, meaning spacecraft and astronauts must endure dramatic temperature fluctuations. In the shadowed areas of space, temperatures can plummet to hundreds of degrees below freezing, while in direct sunlight they can soar to scorching highs. These extremes pose a significant threat to both human life and the functionality of equipment. For astronauts, maintaining a stable body temperature is critical. Prolonged exposure to extreme cold can lead to hypothermia, while excessive heat can cause dehydration and heatstroke. Spacecraft must also be designed to withstand these conditions, as materials can become brittle in the cold or warp under intense heat. Even minor failures in thermal regulation systems could have catastrophic consequences, making this a top priority for engineers. To combat these challenges, spacecraft are equipped with advanced thermal control systems. These systems use a combination of insulation, reflective coatings, and active heating or cooling mechanisms to maintain a stable internal environment. For example, multi-layered insulation blankets are used to protect against the cold, while radiators help dissipate excess heat. Additionally, spacecraft often rotate to distribute heat evenly, preventing any one side from becoming too hot or too cold. Astronauts also rely on specially designed spacesuits to protect them during spacewalks. These suits are equipped with internal temperature regulation systems, ensuring that astronauts can work safely in the harsh conditions of space. Despite these advancements, the risk of equipment failure or human error remains, highlighting the need for constant vigilance and innovation. The extreme temperatures of space also impact scientific instruments and experiments. Sensitive equipment must be carefully shielded and calibrated to function accurately in such conditions. For example, telescopes and cameras used in space missions require precise thermal control to avoid distortion or damage to their lenses and sensors. As we venture further into the cosmos, the challenge of extreme temperatures will only grow more complex. Missions to planets like Mercury or moons like Europa, with their even more extreme environments, will require even more sophisticated solutions. By continuing to develop and refine thermal control technologies, we can ensure that both humans and machines are prepared to face the unforgiving conditions of space. The battle against extreme temperatures is a testament to human ingenuity and resilience. It reminds us that space exploration is not just about reaching new frontiers, but also about overcoming the formidable challenges that come with them. As we push the boundaries of what is possible, we must remain committed to innovation, ensuring that our journey into the unknown is both safe and successful. Now turning to the 10th hidden danger of space exploration, we delve into the critical issue of communication delays. As missions venture further from Earth, the time it takes for signals to travel between spacecraft and mission control becomes a significant challenge. This delay can range from a few minutes to over 20 minutes, depending on the distance, creating a gap that can complicate decision-making, especially during emergencies. For example, during missions to Mars, the average communication delay is around 20 minutes round trip. This means that if an astronaut on Mars sends a message to Earth, it takes about 10 minutes to reach mission control and another 10 minutes for the response to return. In a crisis, such as a sudden equipment failure or a medical emergency, this delay can be the difference between a swift resolution and a catastrophic outcome. Imagine a scenario where a spacecraft's life support system begins to malfunction. On Earth, engineers might quickly identify the issue and provide a solution. But with a 20-minute delay, the astronauts would have to wait for instructions, all while the situation worsens. This lag forces astronauts to rely heavily on their training and onboard systems to handle emergencies independently, adding immense pressure to an already stressful environment. Communication delays also impact scientific operations. When conducting experiments or exploring new terrain, astronauts often need real-time feedback from Earth-based scientists. However, the delay means that adjustments or corrections to experiments must wait, potentially compromising the results. For instance, if a rover on Mars encounters an unexpected obstacle, the delay in receiving new instructions could slow down the mission's progress significantly. To mitigate these challenges, space agencies are developing advanced autonomous systems and artificial intelligence to assist astronauts. These technologies can analyze data, make decisions, and even execute commands without waiting for input from Earth. Additionally, mission planners are designing protocols that prioritize critical communications, ensuring that the most urgent messages are sent and received as quickly as possible. Despite these advancements, communication delays remain a formidable obstacle in space exploration. They remind us that as we push further into the cosmos, we must not only overcome physical challenges but also adapt to the limitations of time and distance. By continuing to innovate and refine our communication technologies, we can ensure that future missions are better equipped to handle the complexities of deep space exploration. Now turning to the 11th hidden danger of space exploration, we explore the perilous challenge of gravity wells. These are the intense gravitational fields surrounding planets, moons, and other massive celestial bodies. Navigating into and out of these gravity wells demands extraordinary precision, as even the slightest miscalculation can lead to disastrous consequences. When a spacecraft approaches a planet or moon, it must carefully adjust its speed and trajectory to enter orbit or land safely. This process, known as orbital insertion, requires exact calculations to ensure the spacecraft doesn't crash into the surface or veer off into space. For example, when landing on Mars, a spacecraft must slow down from thousands of miles per hour to a complete stop in just a matter of minutes. Any error in timing or thrust could result in a catastrophic crash. Exiting a gravity well is equally fraught with danger. To escape a planet's gravitational pull, a spacecraft must reach what's known as escape velocity. This is the speed required to break free from the planet's gravity and continue into space. Achieving this speed demands immense energy and precise engine burns. If the calculations are off, the spacecraft could either fail to escape, leaving it stranded, or overshoot its intended trajectory, potentially sending it hurtling into the void of space. One of the most critical moments in space exploration history that highlights the risks of gravity wells was the Apollo 13 mission. As the spacecraft attempted to return to Earth, engineers had to perform a precise maneuver to slingshot around the moon and use its gravity to propel the crew back home. Any miscalculation could have left the astronauts lost in space or sent them crashing into the lunar surface. The success of this maneuver was a testament to the skill and precision required to navigate gravity wells safely. The dangers of gravity wells are further compounded by the unpredictable nature of space. Factors like gravitational anomalies, uneven terrain, and atmospheric conditions can complicate calculations and increase the risk of errors. For instance, the thin atmosphere of Mars creates unique challenges during descent, as it provides just enough drag to require careful adjustments, but not enough to slow the spacecraft significantly. To mitigate these risks, space agencies rely on advanced computer simulations, precise navigation systems, and redundant safety measures. Engineers meticulously plan every aspect of a mission, accounting for every possible variable. However, even with the best technology and planning, the inherent unpredictability of space means that gravity wells will always pose a significant threat to space exploration. As we continue to venture deeper into the cosmos, mastering the art of navigating gravity wells will remain a critical skill. It's a reminder that space exploration is not just about reaching new frontiers, but also about overcoming the invisible forces that shape our journey through the universe. Now turning to the 12th hidden danger of space exploration, we delve into the critical issue of spacecraft design flaws. Even the most advanced spacecraft, engineered with cutting-edge technology and meticulous planning, can harbor hidden weaknesses that only reveal themselves in the unforgiving environment of space. These flaws, often undetected during ground testing, can lead to catastrophic failures, jeopardizing missions and endangering lives. One of the most infamous examples of a design flaw in space exploration history is the Space Shuttle Challenger disaster. In 1986, the shuttle disintegrated just 73 seconds after liftoff, claiming the lives of all 7 crew members. The tragedy was traced back to a faulty O-ring seal in one of the solid rocket boosters, which failed to withstand the unusually cold temperatures on the morning of the launch. This flaw, though identified by some engineers beforehand, was not adequately addressed, highlighting the devastating consequences of overlooking even the smallest design detail. Another example is the Mars Climate Orbiter, which was lost in 1999 due to a simple but critical error in unit conversion. The spacecraft's navigation team used metric units, while the software controlling its thrusters operated in imperial units. This mismatch caused the orbiter to descend too close to Mars' atmosphere, where it burned up. The incident underscored the importance of clear communication and rigorous testing in every aspect of spacecraft design. Design flaws can also emerge from the unique challenges of space itself. For instance, the Hubble Space Telescope, launched in 1990, initially suffered from a flaw in its primary mirror. The mirror had been ground to the wrong shape, resulting in blurry images. While this issue was eventually corrected with a servicing mission, it demonstrated how even a minor error in design could compromise the success of a billion-dollar project. To mitigate these risks, space agencies employ rigorous testing protocols and incorporate redundancy into spacecraft designs. Redundancy means having backup systems or components that can take over if the primary ones fail. For example, the International Space Station is equipped with multiple layers of redundancy in its life support systems, ensuring that a single failure doesn't endanger the crew. Additionally, engineers conduct extensive simulations and stress tests to identify potential weaknesses before launch. Despite these precautions, the complexity of spacecraft and the unpredictable nature of space mean that design flaws can still slip through. This reality underscores the need for continuous improvement in engineering practices and a commitment to learning from past mistakes. As we push the boundaries of space exploration, addressing design flaws will remain a critical challenge, reminding us that the journey to the stars is as much about perfecting our technology as it is about daring to explore. With the next phase of the journey in sight, we now turn to the 13th hidden danger of space exploration, where we'll examine the role of human error in shaping the outcomes of missions. Now turning to the 13th hidden danger of space exploration, we explore the critical role of human error in shaping the outcomes of missions. Even with the most advanced technology and meticulous planning, the human element remains a variable that can introduce unexpected risks. From miscalculations to procedural mistakes, human error has played a part in some of the most significant challenges and tragedies in space exploration history. One notable example is the Apollo 13 mission in 1970. While the mission is often remembered for its successful return to Earth despite an oxygen tank explosion, the incident itself was triggered by a series of human errors. During routine maintenance before the launch, a technician failed to properly secure a switch, which led to the tank's insulation being damaged. This oversight, combined with the decision to use higher voltage equipment during testing, created the conditions for the explosion. The crew's survival was a testament to their ingenuity and teamwork, but it also highlighted how even small mistakes can cascade into life-threatening situations. Stress and fatigue further amplify the risk of human error. Astronauts operate under immense pressure, often working long hours in high-stakes environments. The mental and physical toll of space travel can impair judgment and slow reaction times, increasing the likelihood of mistakes. For instance, during the Skylab 4 mission in 1973, the crew experienced significant fatigue due to an overly demanding schedule. This led to errors in data collection and communication with mission control, prompting a re-evaluation of workload management in space missions. To minimize the impact of human error, space agencies have implemented several measures. One key strategy is the use of standardized procedures and checklists, which help ensure that critical tasks are performed correctly and consistently. These tools reduce the reliance on memory and provide a clear framework for decision-making, even under stress. Additionally, extensive training and simulations prepare astronauts and ground crews for a wide range of scenarios, helping them develop the skills and confidence needed to handle emergencies. Another important measure is the emphasis on teamwork and communication. Clear, open communication between crew members and mission control is essential for identifying and addressing potential errors before they escalate. For example, the International Space Station operates with a culture of transparency, where crew members are encouraged to report concerns or mistakes without fear of judgment. This collaborative approach fosters a safer and more resilient environment. Despite these efforts, human error remains an inherent risk in space exploration. The complexity of missions, combined with the unpredictable nature of space, means that mistakes can and do happen. However, by learning from past incidents and continuously improving training and protocols, space agencies can reduce the likelihood of errors and enhance the safety and success of future missions. As we move forward, the next hidden danger we'll examine is the lack of immediate medical care in space, a challenge that underscores the importance of preparedness in the face of unforeseen emergencies. Now turning to the 14th hidden danger of space exploration, we delve into the critical issue of the lack of immediate medical care in space. Unlike on Earth, where medical emergencies can be swiftly addressed with hospitals and trained professionals just minutes away, astronauts in space face a stark reality. In the event of an injury or illness, immediate care is simply not an option, and the limited resources available onboard spacecraft add another layer of complexity to this challenge. One of the most significant hurdles is the microgravity environment, which complicates even the most basic medical procedures. For example, administering an injection or performing CPR requires techniques that differ drastically from those used on Earth. Fluids behave differently in microgravity, making it harder to control bleeding or distribute medications effectively. Even something as routine as diagnosing an illness becomes more difficult, as symptoms like swelling or fluid retention can present differently in space. The medical kits carried on spacecraft are designed to handle a range of emergencies, from minor injuries to more serious conditions. However, these kits are limited in scope and cannot replace the comprehensive care available on Earth. Astronauts receive extensive medical training to handle emergencies, but they are not doctors, and their ability to treat complex conditions is inherently constrained. For instance, during the Apollo program, astronauts had to rely on basic medical supplies and their own ingenuity to address potential health issues, knowing that a return to Earth for treatment could take days. The International Space Station has improved upon this with more advanced medical equipment, including ultrasound devices and telemedicine capabilities. These tools allow astronauts to consult with medical professionals on Earth in real time, providing guidance for diagnosis and treatment. However, even with these advancements, the ability to perform surgeries or manage severe trauma remains severely limited. In the event of a life-threatening emergency, such as a heart attack or severe injury, the crew would face significant challenges in stabilizing the patient until a return to Earth could be arranged. Another concern is the long-term health effects of space travel, which can complicate medical care. Conditions like spaceflight-associated neuroocular syndrome, or SANS, which affects astronauts' vision, and the weakening of bones and muscles due to prolonged exposure to microgravity, require ongoing monitoring and management. These issues highlight the need for robust medical protocols and preventive measures to mitigate risks before they become emergencies. As we look to the future of space exploration, particularly missions to Mars and beyond, the lack of immediate medical care becomes an even more pressing concern. The farther astronauts travel from Earth, the longer it will take to return in an emergency, making self-sufficiency and advanced medical capabilities essential. Researchers are exploring innovative solutions such as 3D printing of medical supplies and the development of autonomous medical systems to address these challenges. However, the reality remains that space is an unforgiving environment, and the risks of medical emergencies are an ever-present danger. With this in mind, the next hidden danger we'll explore is orbital decay, a phenomenon that poses a unique threat to the stability and safety of spacecraft in Earth's orbit. Now turning to the 15th hidden danger of space exploration, we explore the phenomenon of orbital decay, a subtle yet significant threat to spacecraft orbiting Earth. Orbital decay occurs when a spacecraft gradually loses altitude due to the drag caused by Earth's upper atmosphere. Even at high altitudes where the atmosphere is incredibly thin, the cumulative effect of this drag can cause a spacecraft to slow down and descend over time. If left unchecked, this process can lead to uncontrolled re-entry, posing serious risks to both the spacecraft and any potential debris that might survive re-entry. The risks of orbital decay are particularly concerning for satellites and space stations, which rely on precise orbits to function effectively. For example, the International Space Station orbits at an altitude of approximately 400 kilometers, where atmospheric drag is still present. To counteract this, the station must periodically perform reboost maneuvers using thrusters to maintain its orbit. Without these adjustments, the station would gradually lose altitude and eventually re-enter Earth's atmosphere, potentially endangering both the crew and the structure itself. Uncontrolled re-entry is another major concern. When a spacecraft descends too rapidly, it can break apart due to the intense heat and pressure of re-entry. This not only destroys the spacecraft but also creates a shower of debris that can pose a hazard to people and property on the ground. Historical examples, such as the re-entry of the Skylab space station in 1979, highlight the unpredictability of such events. While most debris burns up upon re-entry, larger pieces can survive, making it crucial to monitor and control the descent of defunct satellites and other space objects. The need for periodic adjustments to maintain orbit adds another layer of complexity to space missions. These maneuvers require precise calculations and careful planning to ensure that the spacecraft remains in its intended orbit. For crewed missions, such as those to the International Space Station, maintaining a stable orbit is essential for the safety of the astronauts on board. Even small deviations can have significant consequences, making orbital decay a constant concern for mission controllers. As we look to the future of space exploration, the challenge of orbital decay will only grow more complex. With an increasing number of satellites and space debris in orbit, the risk of collisions and uncontrolled re-entries will rise. Efforts to mitigate these risks include the development of advanced tracking systems and technologies for active debris removal. However, the reality remains that orbital decay is an inherent challenge of operating in Earth's orbit, requiring ongoing vigilance and innovation to ensure the safety and sustainability of space missions. With this in mind, the next hidden danger we'll explore is space weather, a broader phenomenon that encompasses solar winds, geomagnetic storms, and other cosmic events that can impact spacecraft and astronauts. Now turning to the 16th hidden danger of space exploration, we delve into the unpredictable and often invisible threat of space weather. Space weather encompasses a range of phenomena, including solar winds, geomagnetic storms, and solar flares, all of which originate from the sun's activity. These events can have profound effects on spacecraft, satellites, and even astronauts, making them a critical concern for mission planners and scientists alike. Solar winds, for instance, are streams of charged particles emitted by the sun that travel across the solar system. While Earth's magnetic field provides some protection, spacecraft and satellites in orbit are directly exposed to these particles. Over time, this exposure can degrade sensitive electronics, disrupt communication systems, and even alter the trajectory of satellites. For astronauts, prolonged exposure to solar winds increases the risk of radiation-related health issues, such as cancer and damage to the central nervous system. Geomagnetic storms, another aspect of space weather, occur when solar winds interact with Earth's magnetic field, causing disturbances that can affect both technology and human health. These storms can induce electrical currents in power grids on Earth, leading to blackouts and damage to infrastructure. In space, they can interfere with satellite operations, disrupt GPS signals, and create hazardous conditions for astronauts. For example, during a geomagnetic storm, the increased radiation levels can force astronauts to take shelter in shielded areas of their spacecraft, limiting their ability to perform critical tasks. Solar flares and coronal mass ejections, or CME, are among the most dramatic and dangerous space weather events. These sudden bursts of energy and matter from the sun can release massive amounts of radiation and charged particles into space. If directed toward Earth, a powerful CME could overwhelm the shielding of spacecraft, damage satellites, and pose a severe threat to astronauts. The Carrington event of 1859, one of the most intense geomagnetic storms ever recorded, serves as a stark reminder of the potential devastation. If a similar event occurred today, it could cripple global communication networks and power grids, highlighting the need for robust monitoring and prediction systems. Monitoring and predicting space weather events are essential for mitigating their impact. Organizations like the National Oceanic and Atmospheric Administration, or NOAA, and NASA operate satellites and ground-based observatories to track solar activity and provide early warnings. These systems allow mission controllers to take preventive measures such as adjusting satellite orbits, powering down sensitive equipment, or delaying launches during periods of heightened solar activity. For astronauts, real-time data on space weather can mean the difference between safety and exposure to dangerous radiation levels. As we continue to explore the cosmos, understanding and preparing for space weather will remain a top priority. The Sun's activity is cyclical, with periods of increased solar storms occurring roughly every 11 years. During these peaks, the risks to spacecraft and astronauts are significantly higher, requiring heightened vigilance and advanced protective measures. By investing in research, technology, and international collaboration, we can better predict and respond to space weather events, ensuring the safety and success of future missions. With this in mind, the next hidden danger we'll explore is the psychological effects of long-term isolation, a challenge that tests the mental resilience of astronauts as they venture deeper into the unknown. Now turning to the 17th hidden danger of space exploration, we explore the profound psychological effects of long-term isolation. As astronauts venture deeper into space, far from the familiar comforts of Earth, they face not only physical challenges but also significant mental and emotional hurdles. The isolation of space can weigh heavily on the human mind, testing the resilience of even the most seasoned explorers. One of the most immediate challenges is the impact on individual mental health. Being confined to a small spacecraft or space station for months or even years can lead to feelings of loneliness, anxiety, and depression. The absence of natural light, the constant hum of machinery, and the lack of personal space can exacerbate these feelings, creating a sense of detachment from reality. For some astronauts, the psychological strain can manifest in subtle ways, such as irritability or difficulty concentrating, while for others, it may lead to more severe mental health issues. Team dynamics also play a crucial role in the psychological well-being of astronauts. In such close quarters, even minor disagreements or misunderstandings can escalate, potentially jeopardizing the success of the mission. The pressure to perform under extreme conditions, combined with the lack of privacy, can strain relationships among crew members, Maintaining open communication and fostering a sense of camaraderie are essential for preventing conflicts and ensuring a cohesive team environment. To address these challenges, space agencies have developed various strategies to support the mental health of astronauts. Regular communication with loved ones back on Earth, for example, provides a vital emotional lifeline. Video calls, emails, and even recorded messages from family and friends can help alleviate feelings of isolation and remind astronauts of their connection to home. Additionally, structured routines and schedules provide a sense of normalcy and purpose, helping to combat the monotony of life in space. Another key strategy is the inclusion of recreational activities and personal downtime. Astronauts are encouraged to engage in hobbies, exercise, and even watch movies to break up the routine and reduce stress. These activities not only improve morale, but also help maintain cognitive function and emotional stability. Furthermore, psychological support systems such as counseling sessions with mental health professionals on Earth are available to astronauts throughout their missions. These sessions provide a safe space for crew members to express their concerns and receive guidance on managing stress and anxiety. As we look to the future of space exploration, particularly missions to Mars and beyond, the psychological effects of isolation will remain a critical concern. The longer the duration of the mission, the greater the need for innovative solutions to support mental health and team cohesion. Advances in virtual reality, for instance, could offer astronauts immersive experiences that simulate the sights and sounds of Earth, providing a temporary escape from the confines of their spacecraft. Similarly, artificial intelligence could be used to monitor the emotional well-being of crew members and offer personalized support when needed. By prioritizing the psychological health of astronauts, we can ensure that they are not only physically prepared for the challenges of space, but also mentally equipped to handle the unique demands of long-term isolation. As we continue to push the boundaries of human exploration, understanding and addressing these hidden dangers will be essential for the success and safety of future missions. With this in mind, the next hidden danger we'll explore is the limitations of current radiation shielding technologies, a critical factor in protecting astronauts from the harsh environment of space. Now turning to the 18th hidden danger of space exploration, we delve into the critical issue of radiation shielding limitations. As astronauts venture beyond Earth's protective atmosphere, they are exposed to high levels of cosmic radiation, a constant and invisible threat that poses significant risks to their health. While current shielding technologies offer some protection, they are far from perfect, leaving astronauts vulnerable to the harmful effects of radiation. Cosmic radiation consists of high-energy particles from the Sun and distant galaxies, capable of penetrating spacecraft walls and damaging human cells. Prolonged exposure can lead to serious health problems, including an increased risk of cancer, damage to the central nervous system, and even long-term cognitive decline. The challenge lies in creating shielding that is both effective and practical, as the materials needed to block radiation are often heavy and bulky, making them difficult to incorporate into spacecraft design. Current shielding methods primarily rely on materials like aluminum, which provide some protection but are insufficient against the most energetic particles. Additionally, these materials can produce secondary radiation when struck by cosmic rays, creating another layer of risk. This limitation highlights the need for innovative solutions that can offer better protection without adding excessive weight or complexity to spacecraft. Researchers are actively exploring new materials and technologies to address these challenges. One promising approach involves the use of hydrogen-rich materials such as polyethylene, which are more effective at absorbing radiation. Another area of focus is the development of active shielding systems, which use electromagnetic fields to deflect charged particles away from the spacecraft. While these technologies are still in the experimental stage, they hold great potential for improving radiation protection in future missions. Another avenue of research is the study of biological countermeasures, such as medications or supplements that could help mitigate the effects of radiation on the human body. By combining advanced shielding with medical interventions, scientists hope to create a multi-layered defense system that minimizes the risks to astronauts. As we prepare for longer missions to destinations like Mars, the limitations of current radiation shielding technologies remain a pressing concern. The journey to the Red Planet, for example, would expose astronauts to significantly higher levels of radiation than those experienced in low Earth orbit. Without significant advancements in shielding, the health risks associated with such missions could be prohibitive. By investing in research and innovation, we can develop more effective solutions to protect astronauts from the dangers of cosmic radiation. As we continue to push the boundaries of human exploration, addressing this hidden danger will be essential for ensuring the safety and success of future missions. With this in mind, the next hidden danger we'll explore is the specific health risks to astronauts' vision, a lesser-known but critical challenge of long-term space travel. Now turning to the 19th hidden danger of space exploration, we shift our focus to the long-term effects on astronauts' vision, a lesser-known but critical challenge of extended space travel. One of the most concerning conditions linked to prolonged time in space is spaceflight-associated neuro-ocular syndrome, often referred to as SANS. This condition involves changes in the structure and function of the eyes and brain, leading to vision problems that can persist even after astronauts return to Earth. SANS is believed to be caused by the redistribution of bodily fluids in microgravity, which increases pressure inside the skull and around the optic nerve. This pressure can cause the optic nerve to swell, leading to blurred vision, difficulty focusing, and in some cases permanent damage to the eyesight. Studies have shown that these changes can occur within just a few weeks of being in space, and the effects may worsen over time, especially during long-duration missions. The potential long-term consequences of SANS are significant. Astronauts who experience these vision changes may face challenges in their daily lives, from reading and driving to performing complex tasks that require precise visual coordination. For future missions to Mars or beyond, where astronauts could spend years in space, the risks to vision health could become a major obstacle to mission success and crew well-being. To address this issue, researchers are working to better understand the underlying causes of SANS and develop strategies to prevent or mitigate its effects. One area of focus is the use of specialized equipment, such as lower body negative pressure devices, which help counteract fluid shifts by simulating the effects of gravity. Another approach involves monitoring intracranial pressure and eye health more closely during missions, allowing for early detection and intervention. Additionally, scientists are exploring the role of diet and exercise in reducing the risk of SANS. Certain nutrients, such as antioxidants and omega-3 fatty acids, may help protect the eyes from damage, while regular exercise could improve circulation and reduce fluid buildup in the head. These measures, combined with advancements in medical technology, could provide a more comprehensive approach to safeguarding astronauts' vision. As we prepare for the next era of space exploration, understanding and addressing the risks to vision health will be crucial. The journey to Mars, for example, will require astronauts to spend extended periods in microgravity, making it essential to develop effective countermeasures to protect their eyesight. By investing in research and innovation, we can ensure that astronauts are not only able to explore the cosmos, but also return to Earth with their health and vision intact. With this in mind, the next hidden danger we'll explore is the ethical and legal challenges of space exploration, a complex issue that could shape the future of humanity's presence beyond Earth. Now turning to the 20th hidden danger of space exploration, we delve into the ethical and legal challenges that come with venturing beyond Earth. As humanity reaches further into the cosmos, questions about ownership, responsibility, and cooperation become increasingly complex. One of the most pressing issues is the ownership of extraterrestrial resources. Who has the right to mine asteroids or harvest materials from the Moon or Mars? While some nations and private companies are already planning such ventures, there is no clear international framework to govern these activities. This lack of regulation could lead to conflicts over resource claims, potentially sparking disputes between nations or corporations. Another critical concern is the responsibility for space debris. With thousands of satellites, spent rocket stages, and other fragments orbiting Earth, the risk of collisions is growing. These collisions can create even more debris, leading to a dangerous cycle known as the Kessler syndrome. The question of who is responsible for cleaning up this debris and how to enforce such responsibilities remains unresolved. Without effective solutions, the accumulation of space debris could render certain orbits unusable, jeopardizing future missions and even endangering astronauts. The ethical dilemmas of space exploration also extend to the treatment of extraterrestrial environments. Should we prioritize preserving the pristine conditions of other planets and moons, or is it acceptable to alter them for human benefit? For example, terraforming Mars to make it habitable for humans could have irreversible consequences for any potential native life forms. These decisions require careful consideration of both scientific and ethical principles, balancing the desire to explore and expand with the need to protect and respect the unknown. International cooperation is essential to addressing these challenges. Space exploration is no longer the domain of a few superpowers. It involves a growing number of countries and private entities. Establishing clear guidelines and agreements will be crucial to ensuring that space remains a shared resource for all humanity. Organizations like the United Nations have already begun working on treaties and frameworks, but much more needs to be done to keep pace with the rapid advancements in space technology. As we look to the future, the ethical and legal challenges of space exploration will play a pivotal role in shaping humanity's presence beyond Earth. How we navigate these issues will determine whether space becomes a source of conflict or a platform for collaboration and discovery. By fostering open dialogue and cooperation, we can create a framework that ensures the responsible and equitable use of space for generations to come. With this in mind, we conclude our exploration of the 20 hidden dangers of space exploration, each a reminder of the complexities and risks that come with venturing into the unknown. As we reach for the stars, we must also prepare for the unseen challenges that lie in the void. Which of these dangers do you find most concerning? Share your thoughts in the comments below, and don't forget to subscribe for more space-related content. Until next time, keep looking up. Now turning to the conclusion of our journey through the 20 hidden dangers of space exploration, it's clear that venturing beyond Earth is far more complex and unpredictable than it may seem. From the invisible threat of cosmic radiation to the ethical dilemmas of extraterrestrial resource ownership, each danger reminds us that space is not just a frontier of opportunity, but also a realm of profound challenges. These risks, whether physical, psychological, or legal, highlight the need for careful planning, innovation, and international cooperation as we push the boundaries of human exploration. As we reflect on these dangers, one thing becomes evident: space exploration is not just about technology and ambition, it's about responsibility. The decisions we make today will shape the future of humanity's presence in space, determining whether it becomes a source of conflict or a platform for unity and discovery. The challenges we've explored are not insurmountable, but they demand our attention, creativity, and collaboration. So, as we reach for the stars, we must also prepare for the unseen challenges that lie in the void. Which of these dangers do you find most concerning? Is it the threat of space debris, the psychological toll of isolation, or the ethical questions surrounding extraterrestrial life? Share your thoughts in the comments below. We'd love to hear your perspective. And if you've enjoyed this deep dive into the hidden risks of space exploration, don't forget to subscribe and hit the notification bell for more space-related content. Until next time, keep looking up and remember, the cosmos is as full of mysteries as it is of wonders.